Hello, everyone, and thank you for joining us today. My name is Renee Eveland, and I will be your host for this NASA Technology Transfer Program webinar on NASA's real-time optical receiver project that we sometimes call REALTOR. Our presenters today are Dr. Sarah Tedder and Jennifer Downey. Dr. Sarah Tedder earned a Bachelor of Science degree in Aeronautical Engineering from Purdue University and a PhD in Physics from the College of William and Mary. She spent the first 10 years of her career at NASA working to support research on laser diagnostics, and the last 7 years working in optical communications. Her expertise is in optical hardware with a specialty in fiber optics. Jennifer Downey currently supports the Communications and Intelligence Systems Division at NASA's Glenn Research Center. She received a Bachelor's of Science in Electrical Engineering from The Ohio State University and a Master's of Science degree in Systems and Control Engineering from Case Western Reserve University in 2009. She previously worked on the Space Communications and Navigation Testbed, which is a software-defined radio testbed on the International Space Station. Her primary research interests include software-defined radios and photon-counting optical communications. Following their presentation, I will be giving a short presentation on how NASA licenses technology to outside organizations. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation, so if you have any questions, please type them into the chat box in the lower right corner of your screen, and we will answer them during the Q&A session at the end. And now our presenters will describe their work on NASA's real-time optical receiver project.
Thanks, Renee. So I'm Dr. Sarah Tedder, and I'll get us started today. So we're going to talk about the real-time optical receiver. Jennifer, if you want to go to the first slide. NASA is using the CCSDS Optical Communications High Photon Efficiency waveform standard for future missions, including the examples of O2O, which is the optical Artemis 2 to Orion, which will be flying on Artemis 2 here in a couple years, and then also Psyche, which is a deep space mission. The standard includes ppm 4, 8, 16, 32, 64, 128, and 256 with slot widths from 512 nanoseconds to 125 picoseconds with a maximum data rate of about 2 gigabits per second. NASA Glenn is building a photon counting ground receiver compliant with this standard, and the goal is to have reach all these ppm orders with a maximum slot width of 500 picoseconds and the maximum data rate of 533 megabits per second. The goals of the REALTOR receiver is to utilize commercial off-the-shelf components as much as possible, and to demonstrate with the O2O at the Goddard Low-Cost Optical Terminal ground station, and transfer this technology to commercial companies. You can go to the next slide. So this gives you a graphic representation of our system and how it fits into the bigger picture of the demonstration we're planning coming up soon. So we'll be part of the ground receiver. So we start there behind the telescope with the fiber interconnect, and then which is then connected to the the superconducting nanowires, and that then deliver the signals to the FPGA-based receiver. We've also developed a FPGA-based transmitter, which Jen will talk about later in the slides. You can go to the next slide. So talking a little bit more about each of these subsystems under development. So we actually are working on 2 architectures, which I'll cover in the next couple slides. So for the fiber interconnect, we're looking at both a photonic lantern and or using a few mode fiber. The photonic lantern has a somewhat scalable. You can scale it in terms of the number of legs and therefore the input multimode fiber side. We've been building these in-house under a partnership with the University of Sydney, but there are companies out there that can make these photonic lanterns. The single photon detector is a commercial off-the-shelf detector. It's portable and rack mounted. It's actually comes in one portable rack mounted unit when you order it from them. And Jen will be showing you a picture of that later in the presentation. And there's an array. We are working with two different architectures. One is the array of few mode fiber detect coupled single pixel detectors sharing one cryostat or a single monolithic 16 channel array. It is capable of continuous operation and includes the amplifier electronics and is about 60 to 80% efficient. And then the FPGA-based receiver has one ADC per detector channel, and a digital detector channel combining. We do real-time processing using a COTS development platform. It's compatible with the CCSDS downlink standard, the high photon efficiency, and we're using FPGA VHDL Verilog code, and it will be released once it is done once development is complete and it has been tested. Next slide. So, like I said, we have two architectures. This is the first architecture. It's a photonic lantern to 7 single element detectors. So there in the middle, you can see the green fiber device, which is the photonic lantern in its packaging. The photonic lantern in this case was made with seven seven 6-mode fiber, or few mode fibers that each have 6 modes. And it has a 20 micron graded index core. It makes on one side, it makes a multi-mode fiber input, which is a 55 micron core, and it allows the lantern to support in total 42 spatial modes. You can see a picture of the cross section down there in the left-hand corner, where it looks like a kind of like a bulbous octagon, or sorry, hexagon. And then you can see over on the right a picture of the detectors wired up, and in the lower right-hand corner is a diagram of this system where you can see the photonic lantern uh, collects the light in the multimode fiber side and delivers the light to 7 few mode fibers, and then those are then delivered to the detectors and butt coupled directly to the detectors. Next slide. So this is the other architecture, which is one few mode fiber to a 16 channel SNSPD array. So in this case, we're using a few mode fiber. It's actually a 25 micron graded index core to couple the light into. It supports 10 modes. And then it is butt coupled to a 4LP, a 6-mode fiber. The reason for this is that this architecture detectors were bought back in the time when that fiber was off the shelf. The 4LP fiber was off the shelf, and it is no longer. So we've switched over to the 6LP, um, and these are compatible enough that we're not getting losses, a- and not enough losses to worry about. And so you can see there in the lower left-hand corner is the detector array layout, and there's a blow up of it. You can see multiple colors. So what it is that it is a It's a nanowire, a meandering wire that is broken up into 16 parts. And so it's an array. So each of those colors represent one SNSPD. So we get 16 in one small area. And on the lower right-hand corner, you can see a diagram of the system where we're putting in the optical light and the light into the mode fiber, and then it's coupled to the detector, and then we have 16 channel electrical signals coming out that go to the FPGA. And then Jennifer is going to talk about the FPGA and the transmitter.
Okay, this is a picture of our FPGA-based receiver in the middle there. It's a COTS micro TCA development platform, and we have a command and telemetry interface through HTTP using the Space Telecommunications Radio System architecture. Um, the blue items up top are phase shifters, which we use to time align um, all of the channels coming out of the detectors. Um, so here's a block diagram of what's going on inside of the FPGA-based receiver. So we have two FPGAs. We have the timing recovery FPGA card, and then we have a decoder FPGA card. And then you can see the detectors go through phase shifters and go into an A to D per detector channel into the timing recovery FPGA. So here's some more information on the timing recovery FPGA. So um, it uses a Xilinx radio frequency system on a chip, or RF SoC FPGA, that has 16 A to Ds, which means we can sample up to 16 detector outputs on one board. As I mentioned, we're doing time alignment with mechanical phase shifters. The timing recovery FPGA, it performs channel combining, um, photon counting, symbol timing recovery, code word alignment, and convolutional deinterleaving. And then it calculates the channel statistics and sends the photon counts as well as the channel statistics over to the decoder FPGA. The decoder FPGA then takes in the channel statistics and photon counts and calculates 8-bit slot log likelihood ratios. We're using a BCJR iterative decoding algorithm, and we also perform queuing and reordering for the multiple decoder instances that are required to keep up with the incoming data rates. Um, we also have a separate test mode in the decoder FPGA that allows us to send the photon counts and channel statistics over Ethernet um, uh, in order to test our decoder separately, independent of the rest of the system. Um, we also have a test transmitter, which Sadie mentioned earlier in the presentation, that implements the CCSDS high photon efficiency standard. It's been released on the NASA software release website for anyone to download. So if you're interested in that, it is up there. The receive, VHDL, and Verilog will be up there when we're finished. Um, we send this electrical signal, which is output of the FPGA, into a modulator box, which performs optical pulse carving with two Mach-Zehnder modulators, and there's a picture of that in the lower left there. So we're using this to test our receiver. And so here are some example results, example code word error rate curves for the PPM16 code rate 1/3, 133 megabits per second mode. On the left is the results for the photonic lantern plus the 7 single pixel detector architecture. And on the right is the code word error rate results for the few mode fiber plus the 16 pixel detector array. So as you can see right now, we're measuring about a 0.3 dB implementation loss, which includes the FPGA implementation loss as well as detector jitter. We're measuring about 0.3 for the photonic lantern and about 1.3 dB for the VMware fiber with the 16 pixel detector array. However, um, when we look at the rest of the losses in the system, we expect the two architectures to perform similarly within a few dB. So our next step then is to demonstrate this receiver system at the NASA Goddard low-cost optical terminal. So NASA Goddard will be providing the dome, the telescope, and the back-end optics and the pointing and tracking. And then we'll be connecting our fiber interconnect to the back-end optics and then to the rest of our receiver. And we plan to do this with the O20 mission on Artemis 2. So in conclusion, we have a photon counting ground receiver. We have demonstrated it with several CCSDS HPE modes. We're prototyping two architectures, and the two architectures perform similarly. Um, and I guess our next steps are that we're looking to transfer this technology to a commercial company or several commercial companies, and we're interested in signing a Space Act agreement. And we have listed our email there. And so now Renee is going to talk more about technology transfer and next steps.